Okay, so we are in the home stretch. Unfortunately, we have lost time due to the snow and to testing, and I heard it through the grapevine that we're actually going to lose part of one of the classes this week due to something that might happen. So unfortunately, we got to rush here at the end. It's not the way I like to do things, but it's the hand we've been dealt, and so we got to play it. So game plan for now is to finish up electromagnetic induction. Today we're going to finish that up, the lesson on it, and then we're going to spend whatever remaining time we have today working on the assignment, and then tomorrow in class we're going to work on that assignment. That assignment will be due Wednesday night, but on Wednesday we're going to have to start talking about the very last part of this class. And then I'm going to have the assignment for that last part be relatively short, but encompass all of the topics that need to be assessed on it. It is going to be a new type of circuit involving what are called inductors, which are just solenoids with iron cores, right? But they do something interesting in electric circuits as well. So that'll be the last part. Inductor circuits, inductor resistor circuits, and then inductor capacitor circuits. To make sure we're efficient and make sure we have the maximum amount of time to do review next week, I am going to have you watch Dan Fullerton videos as homework so that we can just focus on the problem solving in class at the end of this week. So on Monday and Tuesday, we'll wrap up the lesson on electromagnetic induction. Then you'll work on the current quest assignment. That was available to you last week, but nobody really started it except for my online students. Oh, okay, and you guys?
I did like 10.
Oh, good. And then you'll also have 3 Dan Fullerton videos to watch by Wednesday. In order to successfully complete today's lesson, we're going to watch the wrap. Well, I'm going to wrap up the lesson on electromagnetic induction, then we'll continue working on that. I also note for extra practice, the progress checks for AP Physics C, Mechanics, and Electromagnetism are now they're live on AP Classroom. You can access those if you want some extra practice. Our review is going to be pretty fast-paced, and it's going to happen mostly next week. Still not sure what we should do for the mock. I would rather not do the mock this weekend because you do have prom, and some of you already have a mock exam this Saturday. Sunday probably wouldn't be best. Would you guys be opposed to doing it after school on 2 days next week? Wait, too many people talking. What?
Miss Fudge has review sessions next week as well. No, it's next week.
Yeah, it's next week.
Tuesday through Thursday next week.
No, it's next week.
All right, well then what about after school sometime this week? Say
Maybe.
Wednesday, Thursday.
This week will not work because
Because I don't want to.
we don't have review sessions Tuesday through Thursday this week.
Oh my gosh.
Who does?
We can just say one of the quests.
Oh, Mr. Little does.
All right, well, I'll figure something out. No, we have to do a mock exam. We have to. So,
Unless we do them Monday. I don't know.
Friday after school, Monday after school.
Let's do it right now, this period.
No, we got stuff to do. Okay, well, we'll figure that out. Anyway, it might have to be after school Friday before school Monday. After school Monday. All right. So thankfully, I didn't have to erase anything after our last lesson, so we can just pick it up from where we left off. We're in the middle of this problem where we had a circular loop, wire loop that has an external field going through the loop, and we have the magnetic field is expressed as a function of time. On that loop, there's a resistor or a light bulb. It could be a light bulb. And we were first asked to find the induced voltage as a function of time, the induced voltage within the wire. And so to do that, we use Faraday's law of electromagnetic induction, which is this guy. The induced voltage is equal to the negative of the derivative of the magnetic flux. And then we also saw that when we kind of incorporated the voltage, right, the equation for the induced voltage, we related it to, let me write it over here. gosh. That was working last week. We also know that the induced voltage, by an equation that we've been using for quite a while for potential difference, is equal to the integral of E dot D. Instead of dr, we use dl when we're talking about actual wire loops or Amperian loops. And so that's also equal to the negative derivative of the magnetic flux with respect to time. Sometimes you might see it that way. And I'll summarize everything with the 4 Maxwell's equations at the end of today. So if you're asked to find the induced voltage, most of the time, the vast majority of the time, you're going to use the derivative of the magnetic flux with respect to time. And so that's what we did here. But we know the magnetic flux, phi b, is the integral over the open surface that's bounded by the wire loop of that integral of b dot dA. And yes, b is changing, but the magnetic flux we want to express as a function of time and then do the derivative. So all we need to do is b dot dA, it's just b dA cosine theta, it's just b dA, because we define our area vectors pointing out parallel to the magnetic field lines. And so the induced voltage is then the derivative of that integral. And whenever we do this integral, it's just b times dA, or the integral of b times dA. B is technically a constant here because this isn't integrating with respect to time. It's integrating with respect to area. So at a particular time, we have the area that is just pi r squared, and we have the magnetic field that, with respect to area, is for that instant in time constant. And so we get the derivative with respect to time is still here, times the magnetic field, times the integral of dA, which is, in this case, is just pi r squared. So that gives us an induced voltage as a function of time of pi r squared times the derivative of this function. So math is simple. Math is simple here. What's difficult is the conceptual idea, right? Faraday's law, but like Mr. Science Asylum said, Faraday's law looks scary, but it's really not that bad. It's really not that bad, as long because students end up seeing the derivative and then an integral, derivative with respect to time, integral with respect to area, and they think that's super complicated. It's like, no, just do the integral with respect to area first. We've been doing that with electric fields for years at this point, integral of E dot dA. So this is the same thing, only we're not going through a surface, in a two-dimensional surface in three-dimensional space. We're just going through an area, right? And then you just do the derivative of that, and it's no big deal. So that's part A. Part A was find the induced voltage. Number B might say something like, these are problems worked out by Mr. Fullerton, by the way. They should be on the notes that you picked up last week. Part B says, all right, find the current as a function of time. Obviously, the voltage, the induced voltage, is changing as a function of time, so we expect the current to be changing as a function of time. If you look on your good old formula sheet, the equation, and remember we have a resistance R here. We assume the resistance of the rest of the wire is negligible. We definitely do have something that relates the current and the voltage. Just because this is not like a battery voltage or a power supply voltage, just because this voltage is generated within the entire loop of wire, doesn't mean that this loop of wire with electricity going through it doesn't obey Ohm's law. Okay, and so we can relate the current and the voltage, and how it's written on your formula sheet. It says I, put this in another color, it says I is potential difference divided by resistance. Right? Well, potential difference is just the voltage driving the circuit. So in this case, we can just say, well, my current as a function of time is going to be the induced voltage as a function of time divided by the resistance R. And that gives us a real easy way to determine an expression for the electric current. And so we just use that. It's going to be the induced voltage, which is pi r squared times 6t minus 2, all divided by the resistance. But we were actually given that it was a 100 ohm resistor. So I could put R there, or I could just replace it with its resistance. We can actually simplify this a little bit, right? If you were in pre-cal with Miss Burke or Miss Garcia, we would want to simplify this a little bit, and we would get pi r squared times 3t minus 1 over 50. Right. Hopefully you can do that reduction in your head. Does your shirt say the boys on it?
Yeah. Or the 7.
Oh, the 7?
Yeah.
It's from the boys, though. I like season 1 better.
Yeah.
Season 1 was phenomenal. Season 2 is alright, but season 1 was,
That's most shows these days.
yeah. Season 1 was great. Okay. What about this? This is where we got to use our noggins a little more. You know, this was pretty easy as long as we know Ohm's law. What if we want to know the direction of the current at t equals 5 seconds? The induced current. I want to know the direction of the induced current at t equals 5 seconds. What would I have to do here?
Well, you have to find the current at t equals 5 seconds.
We'd have to find R.
We have to find the direction.
Wasn't so right.
What dictates the direction of the current?
Oh,
The direction of the induced magnetic field. We know that the external magnetic field points this way, but it's going to vary with time, right? And so we need to know whether the derivative of the magnetic field is positive or negative at t equals 5 seconds.
So you plug it into the magnetic field equation.
Yeah. Well, we do the derivative, right? We do the derivative of the magnetic field to get dB dt
Or 16.
at dB dt is going to be what? 16 minus 2. And so dB dt is the change, the rate of change. If it's negative, that means that the external field is getting weaker, right? Which means the induced magnetic field would be pointing towards you guys. And by the right-hand rule, that says the current would be going counterclockwise. Right? If it was positive, that means the external field is increasing in strength, which means the induced magnetic field that wants to fight that would be pointing into the board. And if the induced magnetic field points into the board, then the current must be going clockwise, right? By the right-hand rule. So at t equals 5 seconds, dB dt equals 6 times 5 minus 2.
That's too hard.
That's too hard.
Let me look
Oh,
at
it's
this.
times negative 2. Okay.
No.
Yeah, we got to bring up the table for this.
It's 28. Rate of change is positive 28, meaning that at t equals 5 seconds, the magnetic field is increasing in strength. So the external magnetic field that gets generated via electromagnetic induction will be pointing into the board to compensate, to try to fight that change. The external field points into the board. The induced magnetic field points into the board, and by the right-hand rule, that means that the current
It's clockwise.
must be going clockwise.
So, answering that question, would we just say it's going clockwise?
Yeah.
I think the current's going out of the board.
What's that?
So I think the current's going out of the board.
Wrong. All right. Make sense?
Yes.
I want to get through this kind of quick just to give you time to start digging into some problems. I want to be able to help you with as many as we can with the time that we have. But we do have inductor circuits to get to before the end of the class, so we want to kind of do this kind of quickly. So can I erase this problem? No one said no.
Only if you're recording.
Oh yeah, I'm recording.
You recorded the sound?
Probably. Hopefully.
At least they looked at the board and they weren't just staring at a circuit this time.
Wait, I think you might just be taking a bunch of pictures.
Staring
like
at
that.
And syncing those pictures with sound.
Yeah.
Yeah. Yes, I should be. Should be recording sound. All right. this example problem is pretty common. We can make it more difficult by putting the rails at an angle, in which case we'd have to incorporate the gravitational force and decompose the gravitational force at the same time. But the most basic type, this is a rod on rails problem. It's not a practical setup. This is not how we generate electricity, but this is just one way to ensure that we understand how to deal with electromagnetic induction. So let's say I have rails, and they're conductors, conducting rails. And here's my rod, and it is a conducting rod. And now sometimes you might have a resistor connecting these two guys, in which case Ohm's law could be invoked. But for now, since this is our first one, let's just talk about they're connected on the end here, right? And so if I put a voltage right here, if I put a voltage in this, I can get a circular loop of current, okay? And let's say there's a magnetic field that is pointing out of the board within that space. We have an external field that is coming out towards you guys within that space. And we want to figure out, oh yeah, and then we take that rod and we just move it this way with some speed v, some constant speed v. So we have magnets set up in here, and I tried to do a setup like this, and I actually put on my science order form this year some really strong magnets, because then you can actually get this to work. But with the small neodymium magnets I have right now, it's just not strong enough to actually get a measurable amount of current here. But if this magnetic field is strong enough, and I just slide that rod this way, I will generate an electric current in that loop. Because that loop of wire in quotes, because it's really just conducting rods, that loop is going to experience not a changing magnetic field. This is a constant magnetic field. But remember, it's not a changing field that induces the voltage. It is a changing flux. And so as this rod slides this way, the amount of electric field going through the loop, going through that open surface that's bounded by the conductors here, the flux will definitely change. I'll get less flux as it moves, as the rod moves. Does that make sense? And so if I want to figure out the induced voltage, and this is where you choose it. This one we hardly, I won't say never use, but you hardly ever use that one. And again, I'll summarize all of Maxwell's equations here in a minute, and I'll write the whole version of Faraday's law up here. Usually when we're trying to figure out the induced voltage and then induced current, via electromagnetic induction, we usually use this form of Faraday's law. And the negative is essentially in a three-dimensional coordinate system. The negative just tells you what direction the induced voltage will drive electric current. So usually we just kind of leave that negative off while we're doing our calculations. We're talking about the magnitude of the induced voltage. And then we use the right-hand rule and our knowledge of how the induced magnetic field interacts with the actual external field. We use the right-hand rule to figure out what the directions are actually going to be. So now we know here, and so I'll just say the magnitude of the induced voltage is going to be equal to the derivative with respect to time of the magnetic flux, which is changing, but that magnetic flux, at least at this instant in time, is just B dot dA. So we essentially just use the integral to figure out an expression for the magnetic field, and then we just differentiate it with respect to time to figure out the induced voltage. And so here again, B dot dA. Well, what's B dot dA? First of all, I got to define my area vectors. Well, I'll just call it. I'll just say no, that's not a good choice. I'll just do the same thing. I have an area vector that's coming out of the board. such that the magnetic field and the area vector point in the same direction. If the magnetic field was going in, I'd probably say the area vector pointed into the board, just to make sure they're parallel. So that B dot dA, which is B dA cosine theta, just ends up being B dA. Well, I need some dimensions here if I'm going to be talking about the area. So let's say the distance, or the height, what did I do here? Let's say this is length L, this side has length L, and this side just has length X.
Do you do the dimensions inside the wire or inside the rail or the rails?
You can assume that the rails are sufficiently thin, so you just probably right to the center. But yeah, it's a good question, but assume that the dimensions of the rail are small in comparison to the actual area that they're bounding. Now, yes, as the rod slides this way, X changes. So when I integrate B dot dA, dA is going to involve a variable that changes. And then when I do the derivative, that's when I determine what the changing flux is, right? The flux at this instant is B times the integral of dA. And then I do the derivative of that to get the change in the magnetic flux, okay? So I know it's going to be BdA, so the induced voltage, the magnitude of the induced voltage, is going to be the derivative with respect to time of the integral of B dA. And again, at this point, we actually have a field that's not varying. The last problem, the field was varying with time, but we still just assumed it was constant when we did the integral. In this case, the field is constant, so I have the derivative with respect to time. And really, the constant comes out of the integral. It's also constant with respect to time, so it goes out to the front. So I have magnetic field times the derivative with respect to time of the integral of dA. Well, what's dA? That's going to be, yeah, I'm sorry, yes. The integral of dA, well, let me write it like this. B times the derivative with respect to time of the total area, which as we know is X times L, right?
Extra large.
Extra large. Now one of those is constant, right? The L is constant. So I can pull that out too. The induced voltage is then going to be BL. Does X change with time as the rod is sliding to the left?
Yes.
Yeah. So it's BL times dx dt.
That's velocity.
And that's velocity. So it's just bulb. So the induced voltage here is just going to be BL times B. Magnetic field strength times the length times the velocity of the thing.
Is this going to be the case for most rail problems?
That is similar to one of the questions.
Sometimes. You'll get some practice.
You're the one who figured all this out.
Acceleration maybe.
Yeah, I figured all this out.
Acceleration.
In the mid 1800s. What?
Wouldn't acceleration make things a little bit more difficult?
Yeah. I've seen a problem where the rails are at an angle and the rod's sliding down at constant velocity, meaning that we'll get to that. All right, so what about the direction of the induced current?
Good question.
As the rod slides this way, is the flux increasing or decreasing? It's decreasing. And so the induced magnetic field is going to point in what direction? To try to keep it from decreasing. What's that? No, the magnetic field.
Yeah.
Magnetic field has got to be either in the direction of the external or in the opposite direction.
Well, it's going to be in, because it's wanting to decrease it, so it's going to want to compensate more by increasing it. So
Yeah.
it's going to be more out,
So it's going to point towards you.
and so
Yeah.
it's going to go counterclockwise.
So the induced magnetic field is going to point towards you because, again, the magnetic flux is decreasing. If the magnetic flux is decreasing, the magnetic field wants to cause that flux to stay the same. So it's going to be pointing out to try to maintain the same amount of flux. It's not going to succeed, but it's going to try. And if that's the case, pointing out, then I need counterclockwise current. It's weird, right? This stuff's weird. It's complicated. This is literally why, one of the reasons that Heaviside invented vector calculus, to make it, because doing this stuff without vector calculus, I don't know how to do it. I don't know how they did it. It must have been a nightmare, though. Yes, sir.
Did we just get rid of the negative? Oh, it's absolute value.
Yeah. I was just talking about the magnitude. Yeah. So technically, I should say the magnitude of the induced voltage is BLV.
Well, that's why the negative is there though, then, right? Because if the flux is decreasing, then it's negative decreasing, so it'll be an increasing magnetic field.
There you go. I don't care what they say. You're a smart guy.
So technically, yeah, we should do. For
Even
the
though
actual, we should put the negative in front. Since we're dealing with magnets.
Yeah. You just got to make sure that you've defined your coordinate axes in three-dimensional space if you're going to be doing that. All right. So, again, we have one more type of circuit, really technically two, but only one new circuit element that we're going to study, and then this class is over. But summarizing Maxwell's equations, we have Gauss's law, parentheses, for electric fields. And we know that. And this is very similar to what we're using here. What we're using here to determine magnetic flux. It's just the integral over the closed surface, not a closed loop, this is closed surface, a two-dimensional surface within three-dimensional space of E dot dA that equals the enclosed charge, the charge enclosed by that surface, divided by the permittivity of free space, epsilon naught. That's Gauss's law for electric fields. And then it's Gauss's law for magnetic fields, which is the one that we actually use the least, but you do need to understand it from a conceptual standpoint. Gauss's law for magnetic fields says that the integral over any closed surface, just like the one for electric fields.
Are you on the formula sheet?
Yeah.
Okay.
Yeah. Of B dot dA equals 0. Which might make you say, well, how come it wasn't 0 over here? Well, here we are talking about magnetic flux through an open surface, not a closed surface, right? You can have a flat sheet and magnetic flux going through that's not 0. But I can't make a closed surface and have magnetic flux not be 0, because any magnetic field line that's going to go into that surface is going to be coming out on the other side. And since we define going in as being negative flux and going out as being positive flux, the net magnetic flux through a closed surface is always 0. As long as we haven't discovered magnetic monopoles, which we haven't as of now.
Yeah, because we haven't talked about that in this class yet.
That's next week, right?
That's next week. We got for next week.
Cool discovery.
We just talked about it.
Yeah, there we go.
Are we gonna talk about like light or
Save
anything
some
like
room.
that after the test?
Talk about what?
Like light or anything? Optics?
Life?
Optics.
Oh, no, optics isn't part of this class.
Electromagnetic field.
What are we going to do after this?
We can talk about that stuff. It's very fascinating.
Whoa, light.
I'll mention light, actually, because we're talking about Maxwell's equations. Then we get Ampere's law.
So are we not talking about electromagnetic fields?
Not in this class, no.
We're talking about physics, electricity, and magnetism?
Yeah. It's you've really got to know vector calculus to really describe electromagnetic fields. So Ampere's law says that the integral over the closed Amperian loop, which is like our Gaussian surface, it's like our Gaussian surface that's just an arbitrary imaginary surface that we draw in space, of the integral of B dot dl equals the permeability of free space times the current that is going through that closed loop.
What's the subscript on the I?
PEN penetrating the surface. And then we got Faraday's law, which, as Mr. Science Asylum pointed out, really is Heaviside law. Faraday just noticed it and did a little preliminary work with it, but it wasn't until vector calculus was a thing where you could actually summarize all that stuff into a single law. And that says, let me write it exactly as it on the formula sheet. Yeah. That says that the induced voltage in a circuit is equal to the integral of E dot dl. And that shouldn't be, and that's a closed loop, sorry. Remember, this is how we define voltage. So don't let this throw you off. Don't let this make it more complicated than it needs to be. Delta V is literally the negative of the integral of E dot dl. E dot dr, right? Say between two capacitor plates, that's where we get the voltage across capacitor plates, just E times the capacitor spacing D. This is just a definition for voltage. We just drop the negative because we don't have two different points within the circuit where we integrate the electric field in dr, right? Because the induced voltage occurs essentially throughout the entire loop, right? And so we just write the integral of E dot dl, and then that's also equal to, as we showed, the negative derivative of the magnetic flux with respect to time. I think that's how they draw it. Yeah. And then you just got to know that the magnetic flux is just the integral over, sorry, the integral over not the closed surface, the integral over the open surface. So why am I doing that? Open surface defined by the wire, right, of B dot dA. Now, these four equations as written do not technically lead straight to the electromagnetic wave equation. And that's because Ampere's law was fixed by Maxwell. Because this, when you have a current that then gets it, that when you have a current traveling through some closed loop, that current will actually end up, because current and voltage, that current will end up generating a magnetic flux. And that magnetic flux will therefore generate its own, what they call, displacement current. And so you get kind of an oppositely oriented current, and it's really complicated and definitely beyond the scope of this class, but just understand this isn't the full version of Ampere's law. Maxwell had to fix Ampere's law because Faraday's law tells us that current generates a magnetic field, if it's changing, that then must be taken into account, especially if you got alternating current, so you have a changing current. We don't need to worry about that in this class. The problems and questions that you'll deal with, you can just attack with Ampere's law as written that way. Just understand that there's another term to Ampere's law. And when you have that other term, and you do some crazy vector calculus, and you do some crazy stuff, you end up generating an equation that looks like the equation for a wave. And that was Maxwell's big insight. Maxwell was just playing around with these equations, and then he realized, because at this moment, they knew what the wave equation looked like. The wave equation is a differential equation. All waves, whether they're waves through a slinky, waves through water, earthquake waves through the earth, sound waves through the air, all waves obey the same form differential equation. And so what Maxwell realized is that if you recast these, and usually you're dealing with them at that level, you're dealing with the differential form of them and not the integral form that we have here, using that upside down del operator and the cross products and the divergent, or the curls and the divergences. If you do some fancy stuff, you end up with a wave equation. And so that was Maxwell rediscovering light, right? He was just messing around with the 4 equations dealing with electricity and magnetism, nothing about light, and then realized that if you mess with them in such a certain way, you end up generating a wave equation. Meaning that you generate an equation describing waves in the electric and magnetic field, right? Hence, electromagnetic wave. And it turns out that in that equation, you end up with this factor. You end up with this factor when dealing with the equation in just the right place, where you know in the general wave equation, you get a factor that tells you the speed of the wave. And then he determined that that factor is pretty much exactly c, the speed of light. And they knew what the speed of light was before they did this. The guy, I think I forgot their names. Foucault, I think, might have had a... They knew the speed of light. Very, very ingenious experiments that they did in the 1800s to determine what the speed of light was. And Maxwell figured, and mu naught and epsilon naught were well known to a pretty high degree of precision at the time. So Maxwell did this stuff for Maxwell's equations, ended up with a wave equation where that wave was saying there's oscillations in B and E, i.e. oscillations in the electric field and the magnetic field. Those oscillations are perpendicular to each other, hence the cross products and curls. And in the general wave equation that involves the factor for speed, that tells you the speed of the wave, this was there, 1 over the square root of mu naught times epsilon naught. And sure enough, when you multiply those, take the square root, divide 1 by that, you get about 3 times 10 to the 8th meters per second, which was then the known value for the speed of light. And so that was rediscovering, or essentially discovering the actual nature of light. It's actually waves in the electric and magnetic fields, and those waves travel at the speed that they already knew the speed of light was. So that was the big leap. That was the big leap there. That was essentially the discovery of electromagnetic radiation. And maybe tomorrow I'll show you a short video from Science Asylum that kind of because what does that look like? What does an electromagnetic wave look like? What does it really mean? I struggled with that for a long time, and I feel like the Science Asylum has a great video that shows how really it's generated by accelerated charges. That's how all light is. You guys learned in chemistry, you have electrons move in energy levels, and when they de-excite, they emit a photon of light, right? It has to do with kind of the acceleration of the electron as it goes from one point to another. And anytime an electron accelerates, it gives off radiation of a certain frequency. And so I'll show you a brief video tomorrow, at least a clip of the video tomorrow.
If you walk to the other side of the room, are you moving the electrons in your body and they generate radiation?
What's that?
If you walk to the other side of the room, are you moving the electrons in your body enough to generate radiation?
Theoretically, probably.
Radiation.
Okay, so not much time left in class today, but go ahead and crack open that quest assignment, and we'll work on it together tomorrow.
Finish it in class today.
Finish it in class today. It's due at the end of the class, so you got about 8 minutes.
Do you think you could do number 6 in that time?
Let's see. You made me work. Come on, man.
Yeah. I did one though.
Number 6.
Yeah, if you just,
Okay, never mind.
if you look for the sign graph, it's that one.
Alright, never mind. Never mind.
Why is it done?
Because if you look in the equation right above it, it's the sine function. So it's just a sine graph.
Yes, you just and it's sine of omega t. So if omega t is on the x-axis, you're looking for the graph with a period of 2 pi.
Yep.
When omega t is 2 pi, you've gone through one full oscillation.
And it makes a whole bunch of stuff.
Yeah, number 11 has the rod on rails that's at an angle, so we can maybe talk about that tomorrow once you get a little farther along. For small fee. I think these problems are fun. I'm a huge nerd, though. I know you're new to it, so it's probably not as fun. But I think that they're kind of challenging, kind of like little puzzles.
Yeah, I don't think they're that challenging at all.
Well, not everyone's as smart as you, Mr. Nelson. Everyone at home, goodbye. Have a nice day. Don't forget to like and subscribe. Smash that like button.